Okay, let's get started. I don't have that much to say today. There's not that much new material to cover today. So mostly it's about markets and what happened if wind and let's say storage or if renewable storage moves into the market. Now, how would the participants behave? And some open question associated with that, right? So not too much to say here today. So hopefully, we can finish a bit earlier and sunny outside. We're in Seattle, so we can all go out and enjoy some of the stuff. Okay. So let's talk about markets. So last time we talked about markets, and really the market we study in power systems, this clears this right. This finds this clears the generation, demand, and find a price. Right. So this last time we covered that if you have say this is your quantity, this is your price. So you have a demand curve and you have a supply curve and you cross this is a pi star. So this is really your price that everything gets paid at. So another way to look at this is to think of so what I want to say in this class is look at what happens when a system has a lot of wind. Right? So like we can think of, let's say I have a lot of renewables in the system, and how does that impact the market price? And what does that mean for the people who are, for example, the wind producers, right? If you're producing wind. Okay, so let's take a look at that. So the way we're going to model wind, right? The way to model wind into this market is to think of the following model. To say, so we want to integrate wind. But now we're going to take demand to be a given. So we're going to take demand to be a variable, I guess. That's what we're going to say, to be a variable. So instead of crossing those two curves like this, we're going to assume that demand is inelastic. So we're going to assume the demand is inelastic. And what happens when you assume the demand is inelastic is you still have the supply curve. Right? So the supply curve doesn't change. There's still something like this. That's your supply curve. But then the demand, because it's inelastic, it's just this sort of vertical line, right, intersecting the supply curve. So what happens to demand is inelastic. So they're just, there's some fixed demand. So this just intersect the supply curve at some points. Okay. So then we can think of pi as a function of demand. So I normally think pi as a function of demand. Right? So the price is a function of demand B. And then this is demand. So pi is some increasing function in D. Okay. Any questions so far? This model? Right. So last class what we covered was demand has a curve, supply has a curve, you cross two curves. Now we're basically assuming the demand curve is this sort of vertical lines, right? So there's some fixed demand, you have to supply it. Then the demand determines a single number, D, right? D is a single number. The single number determines where on the supply curve you operate at. And then this in turn defines the price, right? Defines the price of the system we're looking at. So this is our model. That's our model. Okay. Then the next one is we're going to look at wind. Wind, now we're going to view this as negative demand. Actually, let's think about how we should weigh wind. Let's think about wind. So if we want to model wind in the system, if we want to model wind in the system, then what is the right way? So if you're a wind producer, and now you are bidding into the system, what is your supply curve? If you're a wind power producer, do you have operation cost if you're a wind? Is there a significant operation cost as wind? Right. So if you're a wind producer, basically, as last time we said, the supply curve doesn't include fixed cost. Right. So there's cost associated with constructing the turbine, constructing the wind farm, all that. But that's really not in the supply curve. So wind has essentially zero operating cost. Okay? Wind has essentially zero operating cost. So the way we model wind now in the system is this is modeled as a reduction in demand. That's a reduction in demand. So that means X units of wind, this translates to D minus X. This is equivalent to, in our model, this is equivalent to D minus X units of demand. Any question about this model? Right, so we're going to look at what happens when X unit, right? When X unit of wind comes in, then equivalently, since wind has no cost, this is free power, right? So if wind is there, it is free power. So this, of course, then you use the free power to supply the demand. So for the rest of the generators, then looks like the demand went down by D minus X. Okay, went down by D minus X. Any questions about this? Okay, so if no question about this, then now let's look at our curve, okay? Now what I want to plot, so now we can define, right? So remember before, we have pi as a function, right? So the price is pi d, or pi d minus x, right, for wind. So x is our x units of wind. So pi d minus x is the price. So we can, so it's easier to define. So this by definition, P of x is pi d minus x. So this is just easier way for us to write things down. So P of x, this is the price at x units of wind. Okay, so if you have x units of wind, this is your price. So this is, I guess, more of, this is really a, by definition, pi d minus x, okay, pi d minus x. So what does the plot look like? X, I say I plot P of x. Is it increasing or decreasing, this function? Does it go up or go down? So is it something like this or something like this? So you have more and more x, does the price go up or does the price go down? right? It has to decrease, right? Price has to go down. Right? Price has to go down. Right? So it goes something like this. Let's say linearly. Let's say linearly down. Right? But the reason is, if you look at, if this is demand, this is pi of demand, this is price of demand. This goes something up like this. But when you have X, wind basically moves demand downward, right? So X moves demand in this direction. So as you have more and more X, as you have more and more wind into the system, the lower the price drops, right? The lower the price goes down. Okay? So is this a problem for wind? Is this something we want to happen? Right? So I guess as people paying for power, right, from a consumer's perspective, then this is good, right? Because you have more wind, price of power goes down, so we pay less. This is great. But if you're looking at from a wind power producer's perspective, then what happens here? If you're a wind power producer, are you happy about this? Are you happy about the price going down as you produce more power? Right, so if you're a wind power producer, you're actually quite unhappy about this. Right? This is saying the more wind produces, the lower the price. The lower the price, actually. So as a wind producer, so what this means is actually wind production may be limited by market prices. Right? Wind production may not be limited by the fact that I have a big wind turbine. I don't have a big enough wind turbine. Rather, wind production may simply be limited because I just don't have that much production. I don't want to produce all that much. So by market prices. By market prices. So this is actually a consequence of market design. And this is an interesting consequence because it says if you can produce power at zero operation cost, so you can at zero operation cost, it's not in your best interest to produce the maximum amount of power that you can. You're actually better off producing a smaller amount because you want to capture the fact that the price is higher when you produce less power. So this is somewhat of a counterintuitive or unintended consequence when we set up the market. So let's do a numerical example. And let's see why this is the case. So if you look at a numerical example, right? So let's put some numbers to this. So this is again our x and px. So let's assume this is 1. Okay, let's assume this is 1. We're going to normalize the price when wind is 0 to be 1. And then let's say this curve is px 1 minus alpha times x. So alpha is the slope of this curve. Okay, of this 1 minus alpha of x. Okay, so the total profit of a wind power plant producing x units is px times x. Right? So remember last time we said in the US, everybody got paid the same amount of money. So last time we said that in the US, everybody gets paid the same amount of money. So then the amount of profit you make is how much you produce multiplied by the price you have. Right? Multiplied by the price you have. Okay. So in this case, our assumption is the price is 1 minus alpha x times x. Okay. So this is your total profit. Of course, as a wind power plant, you want to optimize your profit, right? You want to max your profit. Let's say you have some choice of X. You can, let's say you have some choice and you can maximize over X. So then the power plant solves max X, 1 minus alpha X times X. So this is your maximization problem. So here, right, so we take derivative dx, x minus alpha x squared, 1 minus 2 alpha times x. So x star, the optimal production is 1 over 2 alpha. 1 over 2 alpha. Right? This is your optimal production. So this is the production that maxes profit. Okay? So this is the production that where you get maximum profit at. Okay? So if you get maximum profit at this production value, if you can get maximized profit at this production value here, then the question is, so this is even if the available is larger than 1 over 2 alpha, the power plant right? So even if the available wind is larger than this number, it's not economical to operate at higher levels. At higher levels. So this says, of course, you have upper limit that's defined by nature, is how much power you can produce. But even if nature gives you a lot of power, because the way the market works, as you may not want to produce all that much power, right? So your upper limit may be, by this calculation, is this number 1 over 2 alpha. And if you think about in the actual market, so is this alpha large or small? Right? So if alpha is small, then 1 over 2 alpha is a large number, so that may not matter so much. But in reality, is alpha large or small? Is the slope, right? So we're looking at slope of this line. Is the slope very sharp or is the slope very flat? Right? How does price work? How does price work? If you have more, right? So if you want more power, right? How does the price look? How does the price curve look? So if you look at the actual price curve in practice, so this is again drawing the price as a function of demand versus demand. Okay. This actually starts very low. This starts something like this. Let's draw this in blue. So it actually starts at almost close to 0. Okay. So where does this come from? So why is it close to 0? Why is 0? So you only have a little bit of demand. If you only have a little bit of demand, this is normally produced by something like nuclear or wind. So if this is produced by nuclear or wind, or nuclear, wind, or hydro, so there's actually no cost associated with it. So it's quite low here. And then it jumps up, or settles down a little bit, and then it ramps really quickly once the demand gets to this point. But then what we are looking at as wind is essentially, let's say, right? So more wind, we're fitting this curve. And we're essentially fitting this curve because this is d minus x. Right? So this you can think of as our x coming in. So this is our d minus x. This is essentially the alpha slope. So in practice, alpha is quite large. Alpha is pretty large. And so the price really goes up once you get close to the peak load. Right? So the price for the first, in practice, even for, let's say, the first 50% of load, the price is actually quite low. Then it ramps up. Then by the time it gets to a system peak, it really ramps up really, really fast, like right? So it runs fast vertically. But then this is the alpha that enters into this calculation. I think enters into this calculation here. Okay. So what does this say? This basically says, if you are a wind producer, it's actually not to your benefit to produce large amount of wind or even a moderate amount of wind, even if you have the capability. It's to your benefit to produce a little bit, right? You need to make money, so it's px times x. So x cannot be 0, but you produce a little bit to maximize your profit. Because if you produce too much, the price drops too quickly. The price drops too quickly, and then you don't make any money. You don't make money. So to make money, then let's produce only a little bit to take advantage of the fact that the price here is very high. Right. So any questions about this? So, and this actually has happened. This actually happened to actual companies building solar and wind. They set out to build a lot of production capability, but then they found out if they produce a lot, the price actually doesn't work out very favorably for them. The price, if you produce a lot, the price drops very quickly. And sometimes the price is negative, right? The price can be negative. Okay, so you're limited in your production. And then because there's high fixed cost, if the max production you can have is something like 1/2 alpha, and alpha is very large, then it may not make sense for you to build this anyways. You may not be able to make the money back because you have a high fixed cost. So this has happened to actual, investors, who's doing this. So can you think of a way to overcome this? Or not overcome, but in practice, how do you mitigate this impact? Right, so it's obviously to society's benefit to produce as much wind as possible, right? There's to society's benefit to produce up to the capacity that's available. But then how do you convince a wind power to do this? A PPA. A power purchase agreement? Right, okay, yeah. So, right, so success in China is a PPA. So that's right. So in practice, one thing you do is you basically set a fixed payment to wind turbines, right? What you do in practice, you can do is you say, this is a social good. Having a lot of wind is a social good. So I'm going to pay this wind turbine for generating power, even though, economically, it's profit, it makes maximum profit by generating less. And so you create an artificial incentive. You create an incentive to generate power. So in practice, is so often a fixed payment is used to incentivize wind generation. Or a subsidy, right? This is basically a subsidy you give to wind power producers to say, please produce wind. But this subsidies or fixed agreement runs counter to the market notion. Right? We have a market for a reason. And this kind of out-of-market settlements, right? So technically, this is called out-of-market settlement because it's not determined by the price. Right? The price does not reflect this fixed payment you make to wind. So you have this out-of-market settlement to make wind power happy so they can produce a lot. So this is not really this is not really a good design. People are very happy about, right? Because this is not very transparent. How do you negotiate this kind of fixed payment? Why is it at a certain value than some other values? So this is not very transparent. So this is not what market like to do. So a big open question that we have, today is just how do you design this kind of market? We have wind and solar, right? Is a out of market settlement necessary? Do you have to, distinguish basically between power production? Do you have to distinguish between the source of power to settle things out of market? Or is there a better market structure beyond what I show you, the sort of central clearing, central auction-based market structure? Okay, so that is not, so that is a interesting question, interesting debate you are having. Okay, so that's an interesting debate. As if I want to modify the market, so I don't have to do this kind of out-of-market settlements, this sort of uplift settlements, then what is the good way? Right? What is a good way to redesign the market? Right? The market was designed without thinking about renewables at all. There wasn't much idea about renewables. But now we have renewables. We have things with high fixed cost, no operation cost, almost zero operation cost, right? Then how is there a better market? Is there a better market to this? Should we do it like a cell phone plan? Right? Should we do it like a cell phone plan where you just pay a fixed amount to people? And when you use it, you use it however much as you want to use it. Or should we do something else? Or are there better agreements or more transparent agreement you can have with wind? Okay? So this is a question that we don't have a very good answer to. But then if more and more renewables will come online, then the price will tend to drop. Actually, price tends to drop. But then it will drop to a point where it's not economically feasible to build new renewable plants anymore. But then that's a question that we have to think about is how do you make sure people want to build renewable generation? Right? How do you have a market structure that's sort of transparent and they can figure out how much money they'll make? Okay. So there's a sort of avoiding this kind of uplift or out of market settlements as a open question in market design. Okay, it's an open question. We don't know. We don't know what is a good way to avoid this. So if any of you think I have a good idea, please let me know. Please let me know. We don't. There are several people working on this, but there's not a clear way to solve this question. Any questions about this discussion? Okay, so if some of you go work for a government agency, a government regulatory agency, then you'll probably be thinking about this. You'll be thinking, spending some time thinking about this. For example, if we go to FERC, you may need to think about what is the right way to do things here. Okay, so this is about pricing. This is about price. This is about price. But another thing I want to talk about is uncertainty. And that has to do with market. How is uncertainty counted? Okay, how is uncertainty counted? So if you look at uncertainty, so this still has to do with wind. Okay, so what uncertainty in markets means is, right, so let's say wind. So remember in our markets, as the markets happen, this is time, in a rolling horizon. So market happens in a rolling horizon. So if this, I say this is the present time, This is the present. This is now, basically. The market is settled at, let's say, hour ahead or day ahead. Right, so market really happens here. Market does not happen as a precise, as the exact moment, right? As at present, because it takes time to clear the market. So you cannot wait until a second before to clear the market for the next second. Right? So you need at least minutes. But normally this is done hour ahead or day ahead. And so you have things operate in this kind of timeline, time scale. So markets are set over here. Okay, market is settled here. And then, so if you're a wind plant, basically, you wouldn't have to determine X. Right? Determine the amount X day ahead or hour ahead. Right? So because market happened day ahead or hour ahead, then if you're a wind power plant, you want to produce X, you have to tell the market. So that means you have to tell it ahead of time. Right? But then of course there's uncertainty. So of course there's uncertainty because we're a wind, right? Everything's random. Things are random here. So there's sort of high uncertainty. Basically, what if X cannot be delivered in real time? Right? So if you promise, let's say your wind turbine, you promise at 2 p.m., I will give you 5 megawatt. But then you always worry because of the randomness we have in the system. What if I cannot? There is no, 5 megawatt. Maybe there's no wind. Maybe there's no wind when 2 p.m. comes along. Right? So then how do you think this is handled? Let's say you're running a market, wind tells you, hey, I'm going to give you 5 megawatt, 2 p.m. Then what do you do if wind at 2 p.m. says, okay, I don't have enough capacity? Wind happens not to be blowing. So there's not, I can't deliver what I promised. Right, so one is, right, so the chat basically suggests that, something needs to make up for this shortage, right? So if you promise this, then you either use a battery, you pay a fee, you turn on a peaker plant. All this comes down to you pay some penalty. Right? So let's say you don't have a battery. So even if you have a battery, you can think of using the battery as some penalty. So this is, so the actual problem, so this is handled through a penalty. So there's normally a penalty. A penalty is put on deviations. So what happens, so the penalty works basically, you can think of something like this, right? So for wind, the profit is actually max X px times X. So this is, X is what you can determine, day ahead or hour ahead. But you have a penalty. The penalty is, so if you don't know this symbol, so it's fine, I'll explain in a minute. This is, so the penalty is normally putting such that, okay, so this is expectation. So what is this? This is expectation over Z. Z is the actual wind power delivered, right? So Z is how much you actually have when it comes time to deliver it. then X is what you promised. So this subtraction means you pay a penalty out of your profit to cover a mismatch between what you promised you're going to do and what you actually did. Okay? And this is expectation is because, again, I don't know Z, right? I don't know what happened in real time. So this is an average. This is an average. So this is, you have a penalty if you don't do what you said going to do. But the issue here, the sort of the drawback of this approach is one tend to produce even less. But because one now is, there are basically two things working against promising a lot of wind power. One is the more I produce, the less money I make. So that's suboptimal. The second is the more I promise, there's a higher chance of me not being able to pay it in real time. Right? If I promise 5 megawatt and I don't pay it, I don't deliver it, I pay a huge penalty. So I may just well say, be conservative and not be conservative and not promise so much. Okay? So this depresses basically the amount of wind that goes into the system. Okay? So this is a market design issue. This has nothing to do with how good a wind power is or how good the things are. This is just a market design issue. This is saying, my market is not so good. My market is not good enough. So any ideas of how to solve this, at least on the uncertainty side? Can you think, let's say you are now a system operator. You want to encourage your wind power plants to do something more, not be so conservative. Can you think of something you can offer them? Can you think of some ways to overcome this? Any ideas? So now you're a system operator and, right? So you get a mandate saying increase renewable penetration. And you're talking to one producer, they're saying, okay, I have these problems, right? If I don't, if I don't do what I said I'm going to do, then I get this huge penalty. So that's why I want to be conservative. I don't want to offer a lot of wind. Can you think of some ways to overcome this? So better forecasting, Nathan says better forecasting. This is close. Actually, what happens in today determines who does the forecasting. Right? So in this method, the implicit assumption is wind is doing its own forecasting because wind is taking the hit for the penalty. Right? You did not do what you promised to do. So right now, a way to solve this is to say, okay, let the system operator do the forecasting. And so wind doesn't do it. So let's say wind is not, let's say, so wind system operator tells wind, look, I'm going to forecast for you. Okay? So do what I said. Plan to what my forecast is. If the forecast turned out to be wrong, then as an operator, I will take the penalty. Okay? Because I made the forecast. So if it's wrong, then the people who did the forecast should be penalized. So the system operator gets penalized, not wind. Right? So wind does not pay that penalty. Okay? So the forecast is done by the system rather than an individual farm or individual turbine. Okay. Right. So that's fine. That's fine. You can do forecast that way. Is there a drawback to this though? Right. So is there a drawback to pushing the forecast? So better. Okay. So before I say that, better forecasting is always helpful. Right? So better forecasting is always a technology that will make everything better. But forecasting better, especially for large scale wind or solar systems, we have so many farms, that's challenging. That's quite difficult to do. That's quite difficult to do. Right? So right now, sort of a lot of policy design is, who does the forecasting? So right now, a lot of forecasting is pushed to the system operator instead of individual participants in the system. But do you see an issue with that? Is there some danger with, the system operator just producing the forecast? Right? Is there an issue with a central agency that producing this forecast? Right. So the danger there with the central agency producing the forecast is what happens is you may sometimes have this sort of herding behavior. So when you're forecasting this sort of hard, very uncertain events, there is often a systematic bias that's in the forecast. Right? So the system operator sometimes have this systematic bias or a common bias that shows up in their forecast. And if everybody is using that forecast, then now creates a herding behavior in the system, and where everybody makes the same error. So this tends to happen, for example, when the system operator try to forecast things like peak versus non-peak, loss of wind versus no wind. Right? Because if the system let's say the system operator makes error on forecasting, let's say the peak. Right? So system operator says it's not a peak, it's actually a peak. But then since everybody trusts that forecast, we all see the same forecast. We all operate believing that's a correct, right? So we're all believing that's what will happen. Then it turns out if the actual situation is different than the forecast, then nobody is prepared. Right? There's a common error, there's a common mode error that happens where there's only one entity doing forecasting. And so that's a risk you run into if everything is pushed to system operator, right? So if there's only one person doing one entity doing the forecast. So that's another challenge with this sort of market design. Who should do the forecasting, right? If it's wrong, should you penalize people for being wrong? Or should you actually incentivize them to do the best forecast they can do, even though it will be wrong sometimes or be wrong most of the time, right? How do you evaluate people's performance if there's inherent uncertainty associated with it? So if there's an uncontrolled uncertainty associated with it, then how do you evaluate performance? How do you judge wind turbines? How do you say, are they good or bad? Okay. So that's the question we have in market design. Okay. So here, what I'm saying is this should not really discourage you from doing this, right? Rather, you should be very happy. There's a lot of unanswered questions. There's a lot of opportunity now in this space to come up with new approaches. Or if you want to make money, there's a lot of opportunity to actually make money in this space, right? Because there's open questions and there's trade-offs that we don't know how to make. Okay. So again, if this something interesting to you, you can think about this. Think about how. Right? So if you look at the bulk of the course was physically how do I make a turbine. That today, in some sense, is less important to say how do I design a good market that encourages wind. And we are pretty good at physically making turbines. We're very good at it. We're less good at coming up with market rules and regulations and policies of integrating them into the system. Okay, so that's something to think about. Right, so this is for wind. Any questions about this? Okay, so if now let's take our break now. Then we'll come back, we'll look at storage. Okay, so this is for wind, we'll look at what happens with storage. How does storage enter into a market? And can you make money or not if you have a storage? Okay, so let's take a break. We'll come back at 1:27. Then we'll look at storages in markets. Right, so before going to storage, again, a reminder as the course evaluation as the form is out. You should have all received the email link to it. So if you can, please complete that form and give some feedback. Right? So it looks like, at least for the next, hopefully only for the next quarter, we'll be still teaching online. Right? So again, any feedback with respect to that and how we can do better will be appreciated. Right? So if you have some time, please go and fill that form out. So. Right, so then continuing on with storage, storage is actually harder to model in some sense, at least give an easy model than what. And the reason it's harder to model, this really moves the energy in time, right? Storage is not a net generator of energy. So this moves energy in time. This is a new technology. This is essentially different. Right, it's fundamentally different than other things, other type of things we have. Right? So this has to charge and discharge at different times, and it's sort of net. There's no net generation of generation. And there's no net generation of power. Right? So again, if we talk about renewable penetration and things like that, renewable integration, then storage is necessary, but storage doesn't generate power, right? So for going to 100% renewables, we still need 100% power production. Then storage on top of that, right? So really storage is not, it's complementary to things like solar and wind. It's not a different generation technology. Or often you see in the literature or in the news, storage being talked, almost like a generation technology, right? So if blackout happens, oh, we have storage, then we wouldn't have this problem. Not necessarily. It's not an infinite source of energy you can call up anytime you want, right? That's really not the case, right? Still, you need to decide when to charge it, when to discharge it. Okay? So that's the key thing about storage. Right? So if you're making money, right? So if you want to make profit, through price differences. Right? So the profit you make is basically you want to charge at a lower price, right? You can discharge at. Okay? So that's what you want to do to make money, to make profit at the end. Okay? So then let's look at how this happens. And so if you look at operations, right? So basically the operations here is the constraints we need to care about, operation constraints. Then we have the power, energy, limits, right? So we're limited by some upper and lower bound. We have sort of efficiency, right? So it's not 100% efficient. You lose some power when you charge and discharge. Okay? And so these are the operation considerations. These are the constraints you have taken into account. We have when you think about operation. So if we look at charging and discharging, so mathematically, how do we model these considerations, these sort of constraints, operation constraints? Then we have charging. So both are at time t. And charging is limited by some maximum charging rate. Discharging is limited by some maximum discharging rate. And then we have, right? So we have both charging and discharging. Okay? So both are positive numbers, right? So why can we not? Right? So charging and discharging. But this, if you think about this, this seems to be unnecessary formulation, right? This seems to be a little bit too much trouble. So why not? The net injection. For example, why not just look at something like CT minus DT? Why have, rather than call this, for example, making up an XT? Why not just do this? Why not just add them? Why when you look at most storage formulations, you have an explicit term for charging, another explicit term for discharging. Both are positive amounts, right? But if you look at the battery, right, from the black box, right? If you look at it as a black box, you only read one number out of it, right? Why not just make this a positive and negative variable, right? Why not make a variable with both signs? And why is it that for all the models, people insist on having two numbers? Why not just add them together and say, okay, this is a net injection out of the storage? If I think of what? So what is there a difference between charging and discharging? Is there a difference between these two operations? Right? And the reason that you need two variables is the efficiencies are different. And sometimes quite different between charge and discharge. And so you cannot directly add, actually. Right? So efficiency is meaning that when you charge, and not all the power you buy from the grid goes into the battery, you lose some through the charging process. When you discharge, not all the energy that comes out of the battery goes into the grid. You lose some in that process as well. And it turns out these two efficiencies are not the same for most technologies. Right? So sometimes we're better at charging than discharging, sometimes the other way around. So you really cannot add. Right? For example, if you add them up and say, I have one net, let's say one net kilowatt of power coming out of this, it actually matters how you got this one net kilowatt. Okay, so it matters where does this net come from. Okay, so that's why you have to see two variables, right? You see two variables out of this. So basically, if you look at the efficiencies, these two numbers are not necessarily the same, or often they're not the same. We may be more efficient in one than the other. So I think for electric vehicles, so for electric vehicles, you're more efficient at charging or something. Anyway, so there's a difference between the efficiencies. Okay. Then this creates this is a little bit interesting history of how people try to solve this optimization problem, and then how people figure out, it's actually not a problem. Okay, so there's a little bit of a interesting story of what happened. As was, since you need to have two variables, then of course you need to insist that they cannot happen at the same time, right? So a natural thing people have is, okay, you cannot charge and discharge at the same time. It should not be able. It doesn't make sense to say that the battery is not doing anything. The battery that's not doing anything is not equivalent to say you're charging and discharging the same amount of energy. Right? So that is not. Right. So So you don't want right? So you don't want that to happen. You don't want that to happen. Okay? So then we have to think of some way to encode, right, this into the optimization problem. Remember all this, how you use a battery is you solve a big optimization problem. So you have to encode this constraint, some way analytically into that problem. So can you think of the way to do that? Mathematically, how do I write? Mathematically, how do I write the fact that, right, C and T cannot be both non-zero at the same time? Mathematically, is there a way I can write it so a computer will understand? Can I write an equation that says this? Any suggestions? Say you're programming, let's say Python, right? You cannot write, they cannot chart at the same time. You need to writing symbols that they know of. Adding is not close, it's not add. So what should you do? You don't add them together to enforce it. So given two numbers, also not subtract, given two numbers, right? You multiply, right? You multiply them together. Right, so this comes down to the constraint. Is Ct times dt equals to 0. This is actually the standard mathematical way of saying one of them has to be 0. This is equivalent. The product is 0. That's the equivalent saying one of them has to be 0. Right? So if they're both non-zero, this cannot be 0. So at least one of them is 0. So this is a very natural way of writing it. But then if you write it this way, your computer may understand it. Your computer actually doesn't want to solve this. Okay, so this is a hard constraint. This is not linear. Okay, like the computer will have a very hard time enforcing this constraint. Okay, so this is not a very good constraint to have. Then people thought, okay, then let's, there's another way to do this. There's another way to do this. So this is a hard constraint. Turns out, you can do it through adding, but what you should add is not the chart C and D together. This another way to do this is the following. Let's just say I have this constraint. You introduce a variable, 1. And you add a variable, d max times delta t2. What you do here is you insist that these two has to add to 1, and they have to be 0, 1. Okay, so this is the integer formulation. Okay, so this is the integer formulation because now you add integer constraints. Right, so we're not going to go anywhere near how to solve this kind of problems, but anyways, this is one way you can write it. So your computer likes this better, right? Actually, your computer likes this better. This turns out is the easier interpretation for your computer. This is the easier interpretation. But then what's bad is you have integers. So this is easier. This is sort of can be solved, but not efficiently or not easily. Right, so you need to actually do, there's fairly sophisticated techniques to solve this kind of problem. Okay, so, right, so when we first started modeling storage, I guess this is, let's say 10 years ago or so, and people were struggling a lot with this kind of constraints. As they're saying, okay, I need to model them with different variables because efficiency is not the same, but then I have to enforce this kind of constraints. which results in hard optimization problems, making solve everything difficult. We're having a lot of problems with this. But then people figured out, as actually, you don't need to enforce this kind of constraint. Actually, you don't need to enforce this kind of constraint. Because what can happen as if you look at economic interpretation, naturally, they will never be non-zero at the same time. They will never be non-zero at the same time. Okay, so then people figure out, hey, actually, you don't have to think, you don't have to try this hard. Even if you leave them unconstrained, it turns out one of them will be zero. And the reason there is, if you look at the price, right, let's say as lambda dollar per megawatt hour. And so lambda is positive. Okay. But let's say it costs you some number. Let's say it's some cost. Right? Let's say there's some cost. Then now let's think about what happens here. Right? Let's think about what happens here. Now let's suppose, right? Suppose that you charge and discharge the same amount. Let's say you will do a net trip. You do a net trip, okay, around here. But then let's look at your net trip, the cost. Okay, so if your CT equals to DT, then nothing happened, right? Nothing happened here. But then your net cost, as that's lambda T, right? You bought energy at this time, times the amount you charged by, minus lambda T, you have a discharge coefficient now. Right? You have a discharge coefficient because when you discharge, not all the energy makes it, right? Not all the energy makes it. So you have a coefficient here. Then you can pull this term out. So CT equals DT, this is 1 minus D to D. But the efficiency is less than 1. Right? We do not have perfect batteries. We don't have perfect batteries. So this cost is actually larger than 0. Okay, so economically, if you have a mean cost optimization, one of these variables will naturally turn out to be 0. Actually. So this this is not very rigorous, but a more rigorous analysis will say, if meaning cost without explicitly constraining. And so the story is people tried very hard. People try very hard, to solve this kind of problems, all different kind of formulations. Then notice that, oh, hey, if the price is positive, then it doesn't make economic sense for a battery to do both at the same time anyways. And so you don't need to worry too much about it. You don't need to worry too much about it. So this is a very interesting observation. That's an interesting observation people make. Right? So sometimes economic thinking saves us from the sort of very difficult optimization things we have to try. Okay? So this requires the price to be positive. This requires the price to be positive because what happens is the price is negative. So if your battery and the price is negative, what actually is your incentive to do? Right? So it makes sense. This happens when price is positive. But if the price is negative, if your battery, then what actually do you do? You charge and then what? Right? So you charge, and then basically if it's negative for a significant amount of time, you run this kind of cycles. Just cycle through your battery. Right? Because each round trip costs you some energy loss. You have not 100% efficiency. So actually, if it's very negative, as negative, it's negative for a while, you can actually run this kind of loops. right? You run this kind of round trips to waste energy, to waste energy. Okay, so when negative prices is interesting, right? So negative prices and batteries is actually interesting situation. So that, but this is similar, for example, if you have a negative price, and say you're running a data center, then one way to make money is basically just run empty for loop, or find the most computational intensive equation you can solve, keep solving it. Or what people do is, you just copy paste, files from each disks, right? So this is when price is negative and you have to waste power, then interesting things happen. Actually, a lot of interesting things happen. But anyways, if the price is positive, then turns out the battery will not charge and discharge at the same time. It's a relatively easy optimization to solve. Right, so then if you look at the other dynamics, other things are fairly easy. So this charging dynamics is, so this is SOC is the state of charge. So SOC at time t is SOC at t minus 1 plus the net charge minus net discharge. So this is SOC. Then SOC normally have a constraint. Okay, so normally you have this type of constraint. So B here, this is the max capacity. This is often the safe capacity, right? So so for a battery, the problem is you charge it too full, and then let's say you charge it completely full, and then you try to charge it even a little bit more, then the energy has to go somewhere, and there's a risk of catching fire. It's a very, very full, it's risk of catching fire. So you normally have a safe limit here. And then here as mean, this is bounded away from 0. So it's normally not exactly empty. It's bounded away a little bit from 0. As if it's completely empty, you have sort of very high degradation. So this is to prevent large degradation cost. Okay, so you have this kind of bound, you bound one way from the other. And then another constraint that's not, that may not normally show up as, let's say we're operating for t time steps. Then there is often a requirement that the starting SOC should equal to the ending SOC that you have, right? So this is called the energy no net gain. Because this thing, let's say you're a utility, you're trying to use one battery. And often what you do is you want to make sure at the end of the day, you end up with the same amount of energy storage you had at the beginning of the day. This is often what you do if you're operating this in a utility. Right? So you don't want the carry over effect from day-to-day operation. And that is often, so when in planning or in operation, you want to have a clean start. You want to have always start from the same point. So you avoid, net loss and gain. Okay? Net loss and gain. Okay? So then if you look at the, so if you look at the optimization problem, you can write them all together as an optimization problem. So we're going to look at a case where we have demand plus wind plus battery. Okay, we're going to look at the system cost. Okay, we're going to look at the total system generation cost. How much it costs to operate the system in this setting. So the formulation, the cost, the objective is we try to mean some cost. What this cost is, we're going to sum over the generation cost, sorry, no, generation cost subject to that the load is equal to generation plus wind plus battery, or plus battery operations. So this is quantum optimization we want to solve, and we want to put in and see and we want to put in and see sort of what benefit we can get, right? So here we want to do is we want to do this for more than one horizon. Okay, we want to do this, or this is multiple. Because again, battery moves energy back and forth in time. So really you need to look more than one time instance. You look at more than one time instance to see what happens here. Okay? So then we can solve this problem. So we're going to skip all this for mass. This is a 2-period problem. We'll solve the problem. So at the end of the day, what I want to say is, right, so when you solve the problem, basically, what battery does is battery just moves the load across the time period. You can view this as the battery moving load around. Battery moving load around. And so all it does is shifting load or shifting the net load around between two different time periods. The issue is when you solve it, if you look at the amount of cost you have, is this is a system cost with no wind, no battery. Okay? If you add wind, yes, there's actually a big improvement. There's big improvement in the cost. If you add battery, at even 100% efficient, this is a little bit of an improvement. At the more realistic 90% efficiency, you have about 40 cents of improvement. Okay, you have 40 cents of improvement. So the issue with battery, is that, can you make money, right, out of this, right? So if you buy a battery and you go to a system operator saying, if you use my battery, you need to pay me some money to use my battery. Is that possible? Yes. Do you make a lot of money that way? Probably not. Probably not. Okay, so even though battery can shift things in time, turns out to make money out of this shifting, is far from trivial. So with right now, again, nowadays, since there's big push in making battery technology going into the system, a lot of the effort to understand, if you're an individual investor and you want to buy a battery, is it possible to make money back? Or is it again something that is like building a road or building a bridge, right? So it's a societal initiative, let's say building a battery. Or is this something as an individual investor you buy and you try to make money out of it? That's sort of the debate we're having. Okay, so this is the debate we're having. Right, so if you are a utility and you need the battery for reliability purposes, then sure, you can buy a battery. If you're a private investor or utility, your goal is let me save some money by using a battery, that is difficult. Right? So, and all of this is assuming your battery has no degradation. And we're not even factoring the fact that the battery has some degradation cost. And this is basically saying a perfect battery makes some difference, but maybe not as large as we would like. So how do you design things, right? How do you make things more friendly to batteries, to storage? That's another design question that we have. Right? So we have a question of how do you design the market to be more friendly with wind And then another question is, how do you design all this to be more friendly for batteries to come in? Okay, right? Again, should you just pay batteries? Now, because they are storage, should there be a uplift payment? Or should you still design market rules, but then how do you make sure that a storage just doesn't get run out of the market because you can't make the investment, right, money back? Right? So this is another interesting question we have. Okay? Right, so I think so now is a sort of good time to end the class and think about what we did in this course, right? So this course, we spent a lot of time looking at the physics of designing wind turbine, right? How the electric diagram, the physical, the physics behind the turbine, the equivalent circuit behind the turbine. And that certainly will be, the focus of your final, basically type 3, type 4, will be the focus of your final exam. But then going to the future, if you want to think about, what's the role of wind and how to integrate that into the system, then this sort of market issues are become interesting. It becomes sort of a fun area to think about different strategies. Okay. So with that, we'll end the class, right? So good luck with the final. I'll see you next Thursday for the final, and good luck. So more information will be sent out early next week, right? When exactly is the office hour on Thursday and so on. There'll be more information sent out. But then if no questions, then see you on Thursday.
Thank you.
All right, thanks, guys.